Welcome to this Stat 1793 extra sort of bonus lesson, bonus lecture here. In today's video, what we're going to be talking about is the practice quiz that's been posted to the course website. So what I'm going to be doing is actually solving through all of the questions on the practice quiz. I'll be talking through sort of the thought processes for how to address those questions, sort of what you should have been thinking about, how you might have been able to answer those correctly. Now, before you actually watch this video, I would really encourage that you've tried the quiz for yourself. You're going to get far more out of this if you've actually tried to work through these things. As I've been emphasizing throughout the term, a lot of questions in this course are going to seem easier once you see how they're solved than they would have been to actually solve for yourself, right? And so I would encourage that you actually take this opportunity, try the practice quiz out for yourself, see how you're doing, see where you get stuck, and then watch this back and sort of see, did you get those? Were there the correct things you were thinking about? All of that type of good stuff. But assuming you've done that, we can now start talking through the different options here. So I'll just pull up the quiz. And the quiz format's just like the format of the quizzes in the actual class, right? And so we're going to have 20 multiple choice questions. And so we can actually just open this up, and I'm just going to start sort of walking through question by question here, right? And I'll try to indicate how I might go about thinking about these different questions as we go, but mostly we'll be solving through this quiz together, right? So this first question here, it's asking which of the following is not a random variable, right? And so if we remember, a random variable is always going to be a numeric quantity, and it's going to be a numeric quantity whose value depends on the outcome of some experiment, right? And so what we're looking for when we look through these different options is we're looking for something that's not going to be a random variable. So it's either not going to be a numeric quantity, or it's not going to depend on the outcome of a random experiment, right? So we can go through the different options here, right? The result of rolling a six-sided die, that turns out to be a numeric quantity. Rolling a die is an experiment, so we can immediately rule out option A here. The result of tossing a coin, right? The thing that should jump out to you right here is tossing a coin is going to give you a head or tail. It's not going to give you a numeric quantity, right? And so because of that, we're already thinking B is the correct answer here, right? Because it's not going to be a random variable. But let's look through the other things here. The number of red marbles drawn from a sack of 15 marbles in 5 draws, right? So that's going to be counting up some number of them. That's describing an experiment, right? So this is a random variable. The number of days where it has rained over a given week, well, we could think about observing the days and the weather on those days as sort of the statistical experiment here. And again, we're counting up the number of something, right? So that's not going to be the right answer. And the score that an individual earns on a quiz, well, here we sort of have to be making the assumption that score is going to be, say, something like, 20 out of 20. And if you think about that, then writing the quiz is this statistical experiment here, and so we can rule out E as well. So A, C, D, and E are all numbers. This leaves B as the only option for us here. So the answer to question 1 is B. Question 2 asks, which of the following is best treated as a discrete random variable? So remember, with discrete random variables, we're thinking about random variables that we can actually enumerate all of the possibilities for, right? And so we're thinking about whether there's an infinite number or not, we should be able to start listing through, and we're never going to miss any if we start listing through them, right? We also talked in class about how oftentimes we'll have continuous random variables that might be discrete in sort of the real world, but it's going to be so close to being continuous that that's not going to sort of come into effect. And so here, a good example of that is actually the first option, right? So the height of an individual, we've talked about heights. Heights are normally going to be thought of as being on some interval, right? We're thinking about, say, people are between, 3 and 20 feet tall. That's probably too wide of an interval, but it's sort of any value there. So we can cross out height because it's not going to be discrete. The amount of time it takes for an Olympian to complete a race. Again, time is one of these things that we're always thinking we're measuring continuously, right? Because maybe, it takes them 12 seconds to complete this race, or maybe it takes them 12.01 or 12.2379426, right? Whatever. So there's going to be sort of a continuous range of values that can be taken on. The number of cars passing through a toll booth in an hour, right? Number of cars. We are counting up a discrete quantity. We don't know what the maximum number is going to be, but we know it's going to be 0 or 1 or 2 or 3, right? There's sort of no in between here. So C is going to end up being a discrete quantity. But let's look through the remaining answers and just make sure that nothing else sort of stands out here. The distance to the moon. at a randomly selected time from a given spot on the Earth. Distance is basically height, right? In fact, here it sort of is more obvious why we're going to be thinking about this as a continuous quantity, because we're dealing with sort of far larger numbers, and if we're measuring it in small units, it's going to be even sort of a larger range of values. But and then the volume of water. I'm going to, say that volume is essentially just like the height measured in 3 dimensions, right? So, you could think about, again, is there like 10 liters of water? Is there 10.02 liters of water? Is there, 8.96 liters of water, right? So there's sort of going to be an unlimited continuous supply there. So all of those options except for C are going to correspond to continuous random variables. So the answer is C. All right, so we're through the first 2 questions here. Question 3 says that we have this probability mass function, right? And it's given by this expression here. And we're looking at P of x is equal to k times x plus 3. And x is going to take on a value 0, 1, 2, or 3. And what we want to know is what's the probability that x is greater than 0. So what I would recommend in this case is to actually solve through this question without looking at the answers on the multiple choice questions, right? And I would recommend you do this anytime that you can, right? The first 2 questions we had to sort of see the answers to, but in this question, I could have just asked you this question straight up, and then you should be able to come up with the answer, right? So what do we need? Well, we want the probability that x is going to be greater than 0, right? The first thing that I'll note is that this is going to be the probability that x is greater than 0. Well, if we think about this, that means that x is either 1, 2, or 3, right? Anytime we're dealing with sort of a large event, one of the things we've been saying the whole semester is think about taking the complement. And so we could say that's going to be 1 minus the probability that x is less than or equal to 0. That's the complement, right? And for x to be less than or equal to 0, the only possible value here is x equals 0, right? So we get 1 minus the probability that x equals 0. And so then what we need is we need to plug in 1 minus p of 0, right? And p of 0, if we plug in a 0 here, we're going to get 3 times k. All right? And so what we need to now do is figure out what is this value actually going to be. So what's k? And so if we look at this again, right, we're dealing with this PMF right here. And what do we know about PMFs? Well, the key thing that we know about PMFs is that they're going to sum up to the value of 1. So if we sum from x equals 0 to 3 of p of x, we know we have to get 1, right? And so we can actually just do this, right? So the summation is going to be plugging in 0 gives us 3k. Plugging in 1 is going to give us 4k. Plugging in 2 is going to give us 5k. And plugging in 3 is going to give us 6k, right? And so if you actually add this up, we have 3 plus 4 is 7, plus 5 is 12, plus 6 is 18. So that's going to be 18k. And what we know is that 18k has to be 1, so then k is 1 over 18, right? And if k is 1 over 18, well then when we plug in here, we're going to get the probability is 3 over 18, right? Because we're taking 3 times k, which is the same thing as saying 1 over 6, right? But the thing that I will actually point out here is that I made a slight typo on this line when we were getting here. Got a little bit ahead of myself, got a little bit excited. It's going to be 1 minus 3k, right? And so we're taking 1 minus 1 over 6, and so the total answer is going to be 5 over 6. And so if we come back over here, it's not 1 over 6, it's not 3k, it's not 5 over 7, it is 5 over 6. So D is the correct answer, right? And so any of the times that you can actually just do the calculation, I would advise that you try that. All right, so the last one on this page, we're considering a joint probability mass function of 2 random variables, x and y, and we're given by this expression right here. What is the probability that x equals 2 and y equals 3? Okay. Here, we're just given explicitly the joint probability function, right? And so anytime you want the probability of an intersection, anytime you want the joint probability, all you have to do is you take these values, x equals 2 and y equals 3, and you plug them right into this function here. It's as simple as that. So we first check, are 2 and 3 both between 1 and 5? The answer is yes. Right? And so then what we're going to get is we're going to get that this probability is going to be 1 over 150 times by 2 plus 3, which is 5 over 150. 5 over 150, I believe, should be 1 in 30. Right? And so then we look, is 1 over 30 one of the answers? And it is. It's answer B. Right? So B is going to be our correct answer here. Okay, so when we want the joint probability, if we're given the joint probability mass function, as simple as plugging in to the function there. Okay, so now we're through the first page and go on to the next. So we now have two random variables, a and b, and they have conditional probability mass function given by this expression here. The thing to note that I'll point out immediately, it's always important to pay attention to where we actually have positive probability, right? So what we're saying here is that if b is not in this range and if a is not in this range, then the probability is going to be 0, okay? And so specifically, b is going to be between 0 and a is going to be between 0 and 5. So that might sort of be important. Is it more likely to observe b equals 2 given a equals 3, or b equals 3 given a equals 2? Right? And so what we're asked here, we're asked about conditional probabilities, right? So we want b2 given a3. So that's going to be the probability that b equals 2 given a equals 3. And we want to compare that to the probability that b equals 3 given a is equal to 2. Okay, now we're given the conditional probability function, so we could just plug directly into here. But before we do that, I want to point out the thing that we were just highlighting, right? And that's b has to be between the values of 0 and a. Otherwise, it's going to have 0 probability. So before we even check this, right? b equals 3, a equals 2, does not work in this case, right? This probability is going to be 0 because here b is 3. That's above what a would be, right? This would be b has to be in 0, 1, 2. 3 is not there, so the probability is 0. So we know that this term has probability 0. This one is going to be well defined, and we don't actually have to plug in to notice that over here we're not going to get any zeros, right? So automatically we know that b equals 3 given a equals 2 is the smaller probability. So b equals 2 given a equals 3 has the same probability? No. b equals 2 given a equals 3 is less likely than b equals 3 given a equals 2? No. b equals 2 given a equals 3 is more likely than b equals 3 given a equals 2? Yes. We do not require the other conditional probability. We do not require the marginal probability. We would if we needed to find some joint probabilities. Then we would need that marginal, right? So that's question 5. The answer there is going to be C. All right, so now we're given this joint probability function. The joint probability of two random variables, g and w, is given by 1 over 80. And again, just looking at the range here, w is going to be from 1 through 8, g is going to be from 1 through 10. So they don't depend on each other there. That's nice to know. We're asked about the marginal probability mass function of w. Anytime we want the marginal mass probability mass function, we want to use the process of marginalization, right? So we want to have w here. What that means is we want to sum over all of the possible values for g, right? So we're going to say that the probability mass function of w is going to be the summation over all possible values of g, and so that's going to be from 1 to 10 of the joint probability that w equals little w and g is equal to the g term, right? And so we're going to plug in g equals 1 through 10 into this function. This function's constant, right? And so what we're looking at here, so we're looking at the summation from g equals 1 to 10 of 1 over 80, right? This is just adding 1 over 80 to itself 10 times, or 10 times 1 over 80, right? So that's 10 over 80, which is 1 over 8. Okay, so it's going to be 1 over 8. And then the important thing to note here is that w is going to fall into 1, 2, 3, 4, 5, 6, 7, 8. It's going to have the same restriction there. So we know that the PMF of w has to be 1 over 8 over this range here, right? And so if we take a look here, is it 1 over 80? It is not. Is it 1 over 10? It's not. It's still not 1 over 10. So it's going to be one of these last two. Is w in 1 to 10? Nope. So then E is going to be our correct answer. The probability mass function is 1 over 8 for w in that range. Okay, so now we can take a look at question 7 here. And we're told that we know that the probability mass function, p of x, is equal to p of y for every x and y which are observable. We want to know, is it true that probability x given y is equal to the probability of y given x, where we plug in sort of arbitrary values there? So the thing to note here is we're going to have probability xy of x and y divided by the probability of y. This is going to be our probability of, in this case, x given y, right? And we're going to have probability xy divided by probability of x is equal to the probability of y given x, right? And so we have these two different expressions here. In these expressions, we always know that our numerator is going to be the same, right? Because the joint probability is the same. And of course, probability of x and y is the same thing as the probability of y and x. You can switch that order all the time, right? So those two expressions are exactly the same. And what we're saying is that the probability of y and the probability of x are going to be equal for the different values in here. And so what that means is that we're going to have the blue things be the same as well. And if you take one thing that's the same and divide by another thing that's the same, it's going to always produce things that are the same as well, right? So in this case, we know that if the marginals are going to match across the whole distribution, then the conditionals also have to match across the whole distribution. And so we can come here and say, depends on whether this, well, this is always true, right? So this was never going to be the correct answer because x and y is always equal to y and x. Depends on whether x and y are independent. It does not. Independence doesn't play into this at all. Depends on whether they're identically distributed. We're actually told that they're identically distributed, right? We're told that they have the same probability mass function. No, it will definitely not be the case. Incorrect. So that leaves us with option E. It will definitely be the case. So again, even in this case, we were able to sort of solve the question first and then find the correct answer. All right, so moving on, question 8 here. Suppose that we roll a die n times, labeling the rolls x1, x2, up to xn. What is the joint probability mass function of x1 through xn? So the thing to note here is that these are going to be IID, right? They're independent and identically distributed. Every single one of them has the same distribution. Every single one of them is going to be independent of one another. And we're rolling a die. We're going to assume this is going to be a 6-sided die, right? And so what is the probability mass function for that, right? So if we take px, well, we know that it's equally likely, right? It's going to be 1 over 6 that x comes up any of the values between 1 and 6. And we've seen this come up plenty of times throughout the course so far. Now, whenever you have the independent and identically distributed random variables, then what we're looking for is their joint probability, right? If x1 is equal to little x1 and x2 is little x2 and so forth up to xn. Because of the independence, we can write that as the product of all of their little probability mass functions here, right? So that's probability x1, x2, so forth up to xn. Okay. And what we know is that each one of these is exactly the same thing. And in particular, it's all just 1 over 6. So this right here is going to be 1 over 6 times itself n times, so 1 over 6 to the power of n. And each of the values has to be between the values 1 and 6. So we come over here. Joint probability is 1 over 6. Nope. Joint probability is the summation. Not correct. Joint probability is 1 over 6 to the power of n for all of them in between 1 and 6. That's what we just said. So C is going to be our right answer. Take a look here with the summation up here. The only way that we would ever get the summation up there is if the PMF itself had something up in the exponent, but it doesn't. And we cannot find the joint distribution of independent random variables. That's not going to be the case. The joint distribution is just going to be the product of the marginals. So E is incorrect. C is our correct answer here. All right, let's take a look at question 9. So which of the following experiments will not produce independent and identically distributed quantities, right? So remember, we're checking two different things here. We're checking for independence, which means that they're not sort of related to one another. Knowledge about one doesn't inform knowledge about the other. And identically distributed means that the draws are going to be coming from the same probability distribution, right? So we're thinking about the same probabilistic behavior between them, right? If you flip the same coin over and over again, that's going to be fine. But if you roll a 6-sided die and then a 20-sided die, that's not going to be fine because the 20-sided die has different probabilities than the 6-sided die. So with those two traits in mind, we can look down and start thinking about the different options here. So counting the number of heads in multiple flips of a coin, right? Flip the same coin over and over and over again. so we could count up the number of heads, repeatedly rolling 10 fair dice and taking their sum, drawing cards with replacement from a deck, labeling the suits with the numbers 1, 2, 3, or 4, counting the number of red cards in hands of 5 cards over many repeated hands, or using a thermometer to measure your body temperature throughout the day. Okay, so let's go through these one by one. Number of heads in multiple flips of a coin. If you just count that up and then you were to say multiply, like let's say you flip the coin 10 times and then you repeat that over and over again, that will produce IID variables. Repeatedly rolling 10 fair dice and taking their sum, right? So we roll the 10, we add those up, roll the same 10, add them up again. That's going to be IID. Drawing cards with replacement, that's key, from a deck and labeling the suits 1, 2, 3, or 4. So you take out a card, you look at it, 1, 2, 3, or 4, put it back in, shuffle, take out another card. Same experiment being repeated over and over and over again. Counting the number of red cards in hands of 5 cards. So you deal out 5 cards and then you count up the red cards over many repeated hands. So you deal the 5, you look at how many reds there are, you repeat that over and over again. So IID still. So then it's going to be E as the answer here. And let's think about it. Using a thermometer to measure your body temperature throughout the day, right? You might think this is going to be identically distributed, right? The temperature, you like whether you have a fever or not, it's going to be sort of dependent on the same probability distribution. But the key piece here is that these are not going to be independent. Your body temperature in the morning is going to influence your body temperature in the evening and vice versa. And so E is going to be the problem based on dependence. All right. So that's question 9 out of the way. Question 10. What is the median of a die roll using a fair 6-sided die? Right. So with the median, remember the way that we're always going to be thinking about this is you just start adding up over the possible values from the PMF. And then we want to see when do we cross that 50% threshold, right? And so if we take 1, 2, 3, 4, 5, 6, and we know there's a 1/6 chance at each of these, plug those in sort of roughly speaking. It doesn't matter if it's exactly right. So we start with a 1 and we're at 1/6. We're not at the 50% yet, right? So that's no good. We go to the 2. We've now added 1/6 plus 1/6, 2/6. We're still not there. 3, 1/6 plus 1/6 plus 1/6. It's 3/6. That's exactly 50%. Takes the median equal to 3. Okay. So that's going to be C here. Okay, so now we're halfway through the quiz here, right? So hopefully we're doing well. We'll keep working away at this. In a lottery, there are going to be 200 prizes that have $5, 20 prizes that have $25, and 5 prizes that have $100. If we assume that 10,000 lottery tickets are to be issued, what is the fair price to pay for a ticket? Now remember, when we were talking about fair price, we were talking about the expected value. The idea with the fair price is that if you were to pay that money, then you would expect that if you were to have done this repeatedly over and over, you would never earn or lose money on average, right? So what we need to do is we need to find what's the expected payout, right? And so I'll just say, what's the expected value? So we'll do EV, right? The value of the ticket. And remember, it's the possible values times by the probabilities that those values can take on. So we can take on $5, and the probability that it's a $5 ticket is going to be 200 out of the 10,000, right? So we have 200 out of 10,000 times by 5 plus, there's going to be 20 at $25. So that's going to be 20 out of 10,000 times by 25 plus 5 out of 10,000 times by 100, right? And so that's sort of our expected value formula here, right? And in this case, if you do this, I believe that you should get 20 cents, right? So to plug this into your calculator, you get 20 cents. And that means that the fair price to pay is going to be 20 cents. Right? If you pay 20 cents and then you expect to earn 20 cents, on average, you're not going to make or lose any money. And so we go through the options here and we see that E is going to be 20 cents, right? So option E for question 11. Question 12. What can we say about the range and the IQR of a random variable? Well, let's think about this for a minute, right? The IQR is going to be Q3 minus Q1. And the range is going to be the max minus the min. Okay. Now, Q3 is going to be a point in our data, and Q1 is going to be a point in our data. The max and the min are also points in our data. And the important thing to realize is that the max is always going to be greater than or equal to Q3. And it could be equal to Q3 if we think about sort of there being a really high probability of falling on that same maximum value, for instance. And the minimum is always going to be less than or equal to Q1, right? And again, same thing. If you have like 30% chance of taking on the minimum value, well, then that's both the minimum and Q1 for the way that we've defined these things in class. All right. And so in this case, what do we know? Well, we know that the range is always going to be at least as large as the interquartile range, right? The range cannot possibly be smaller than the IQR. We might know some other things, but that's sort of the thing that jumps out immediately. And so we can start looking at the options here. So the IQR can never be larger than the range, right? Repeat that again. The IQR can never be larger than the range. That's true, right? How would the IQR be larger than the range? It would mean that Q3 would have to be bigger than the maximum, or Q1 would have to be smaller than the minimum. And that cannot possibly happen. And so A is going to be the correct answer, but let's look through the other options here. The IQR is always smaller than the range. That's not necessarily the case, right? You could have Q3 and Q1 equal to the minimum and the maximum. The range can never be larger than the IQR. The range is normally going to be larger than the IQR. The range is always smaller than the IQR, right? And again, that's sort of almost never going to be the case. In fact, it can't be the case. The range won't be smaller. It's at sort of smallest the same size. None of the above is always true. No, the IQR can never be larger than the range, right? So A. A is the correct answer here. All right, question 13. Suppose that a random variable x has variance 8. If the expected value of x squared is equal to 3 times the expected value of x all squared, what is the mean of this random variable, assuming that the probability that x is greater than 0 is equal to 1? All right, so there's a lot of information here, but ultimately what we want to do is we want to figure out what's the mean of the random variable. And so how might we think about this? Well, we're told that the variance is going to be 8, right? And so we want to work with the variance of x, right? The variance of x is equal to 8. We also know that the variance of x is given by the expected value of x squared minus the expected value of x, this whole thing squared. Okay. And the reason that we might like doing this is because we're told that the expected value of x squared is 3 times the expected value of x squared. And so then this right here is going to be 3 times the expected value of x squared minus the expected value of x squared. So if you take that away, we have 3 of something minus 1 of the thing. We have 2 of those left. 2 times the expected value of x squared. Divide both sides by 2. We get 4 is equal to this. And so then the expected value of x has to equal the square root of 4, which is going to be plus or minus 2. And so where does this piece of information, probability of x is greater than 0, come in? Well, you can't have a negative expected value if x is always greater than 0, right? And so what we know is that x has to be positive 2. And so we come here, and the answer is going to be A, positive 2, right? It's not 4, not 8, not negative 2, because x has to be positive. And then we cannot determine this without the probability mass function of x. Nope, we did determine it just from the variance of x. Okay, so another computation question that you could do without sort of seeing the options there. All right, on to question 14. So we're told that a random variable x has this probability mass function here. And what we want to know is what's the standard deviation of x. Okay, so the standard deviation is always going to be the square root of the variance, right? And so what we want is the variance of x, and that's going to be the expected value of x squared minus the expected value of x all squared. Now, the thing that I'll point out here is that we have a symmetric distribution, right? If you look at the expected value here, we're going to get negative 1 times 1 over 8 plus 0, right? Because 0 times anything is going to be 0, plus 1 over 8. Well, this 1 over 8 minus 1 over 8 are going to cancel out. So the expected value of x right here is always just going to be 0 in these cases. And so all we need to do is say that the variance is the expected value of x squared. To find this, right, we can think about taking x squared here is going to be 1, x squared here is going to be 0, x squared here is going to be 1. So then we have 1 times 1 over 8 plus 0 times 3 over 4 plus 1 times 1 over 8. That's 2 over 8. Right, so this is 2 over 8, which is 1 over 4. Standard deviation is going to be 1 over the square root of 1 over 4, which is the square root of 1 over the square root of 2, which is, square root of 1 over the square root of 4, 1 over 2. And so we should have half as A. So 14, the answer should be A, not 1/4, not 0, not 3/4, not 1. Okay. All right, so question 15. We're getting sort of near the end here. So hopefully you're still coming along well. And 15 and 16 actually appear to have to do with the same type of setup, so maybe that'll be helpful for us. Suppose that the expected value of x is equal to mu, and the standard deviation of x is sigma. What is the variance of this term? Okay. Well, what I want to do here is just rewrite this. And I'm going to rewrite this as 1 over sigma times x minus mu, right? 1 over sigma, that's just some constant, minus mu, that's just some constant, right? And so this is going to be ax plus b, where a is 1 over sigma and b is minus mu. And we know the variance of ax plus b is always going to be a squared variance of x, right? And so in this case, a is 1 over sigma, so we get that the variance of x minus mu over sigma is going to be 1 over sigma squared times by the variance of x, which we've called sigma squared. So that's going to cancel out, and we're going to be left with just 1. So A is the correct answer again here. Right, B is incorrect because we'd have to divide by it. You're almost never going to see these types of terms coming up in variances because if you add constants, it doesn't change the variance. Yeah, so we're left with just this one. Okay, if we look at 16, we have this basically the same setup, except instead of the variance, we want the expected value, right? And so we can think about this in exactly the same way, right? This is going to be 1 over sigma x minus mu. Treat this as A, treat this as B. The expected value of ax plus b is A times the expected value of x. And I guess here, and I should make this correction, it doesn't change anything for this question up here. This 1 over sigma actually has to be multiplying on both terms, or, just because it's dividing both terms here, right? So it's 1 over sigma here, 1 over sigma here to do that division. Didn't make a difference with the variance, but you know, is going to make a difference here, so I should correct this. That's going to be 1 over ax plus b, right? And so in this case, we're going to have 1 over sigma times the expected value of x, which is mu, minus 1 over sigma times mu, which is b, right? So that's going to just cancel each other out. We're going to be left with 0. So the answer here should be 0. We have A once more. All right, on to question 17. So in question 17, we have a random variable, x, and we know that its expectation is going to be positive, that its variance is not equal to 0, and then we're taking y to be 3x minus 2, and z to be 2x plus 1. What can we say about the expected value of y and x? Well, in this case, we can actually work this out, right? Or sorry, y and z, not y and x. So the expected value of y is going to be the expected value of 3x minus 2. Right, this is ax plus b. So that's 3 times the expected value of x minus 2. And the expected value of z is going to be 2x plus 1. So, or z is 2x plus 1. So it's going to be 2x plus 1. So 2 times the expected value of x plus 1. Right? And we're not told anything else other than the expected value of x is greater than 0 and the variance is not equal to 0, right? So let's try to compare these two terms here. And the thing to notice is that it's going to depend on the expected value of x, right? So if I plug in, for instance, x equals 0, right? Well, at x equals 0, then we're going to be, or the expected value of x is 0. We're going to be -2 for y and +1 for z. So the expected value of z is going to be bigger. But if I plug in expected value of x equals 100, right? Well, the expected value of x at 100 is then going to be 300 minus 2 is 298, right? 200 plus 1 is 201. So then expected value of y would be bigger. And so we actually can't say in this case which of these two is going to be larger, right? And so the expected value of y will be larger sometimes, but not always. Expected value of z will be larger. Well, again, sometimes, not always. They will have equal expected value. Well, of course, that's not always going to be the case. It could sometimes be the case, right? If you set 3x minus 2 equal to 2x plus 1, you could solve where those two lines cross, and you'll figure out where they'll be equal. We would need to know the variance of x to draw a conclusion. Now, the variance of x is kind of irrelevant here, right? We would need to know the expected value of x to draw a conclusion. That is going to be true. One thing that I'd point out is that actually, if you wanted to compare the variance of y to the variance of z, you'd be in a better spot here, right? Because the variance, the really tough thing that we have is that we have these constants. We don't know how those constants are sort of going to interfere with things. Whereas with the variance, you don't have to think about that plus b term. So that's just something to sort of think about. All right, question 18, almost to the end here. Suppose that we know the expected value of x equals 3. What does that mean? Right? There's a few different ways we've thought about this, but sort of what you want to be thinking about anytime you need to interpret these types of statements is we're thinking about repeating an experiment a whole bunch of different times, and then this is going to be the long run average, right? So if you could repeat this infinitely often, then as you start to do that infinitely often, if you just take your average of all of your different results, then the average of that is going to be 3. Okay? So the most likely value that we observe is a 3. No, that's going to be our mode. If our mode was 3, then that would be the truth. 50% chance to observe a value above 3, 50% chance to observe a value below 3. That's going to be true of the median, not the mean, not the expected value. If we perform the experiment many times, we will observe 3 eventually. This is not going to be the case. Think about the fact that the expected value of a die roll is 3.5. Right? You can roll your die forever. You're never going to see a 3.5. The expected value is still there, right? And so it's not that we're ever going to see the expected value, right? That's not necessarily going to be the case. If we perform the experiment many times, the average of all of the experiments will tend towards 3. That's just perfectly what our definition is. So we know D is going to be the correct option, right? But it's worth taking a look at what E is. If we perform the experiment many times, most of the observations will be around 3. This isn't going to be the case either, right? If you think about, say, a random variable, and half of the time it takes on a value of -100, and half of the time it takes on a value of +100, the mean of that is going to be 0, but it's never going to be near 0, right? So we never have to be near our mean, but we just know that if we're not near our mean, the high values and the low values are going to cancel each other out. So D is the only acceptable option there. That brings us on to question 19. Okay. So the variance of x equals 0, expected value of x is equal to 1. All right. So this is worth thinking about for a second, right? What does it mean for our variance to be 0? Well, our variance is only going to be 0 if things are constant, but can we show that another way? Well, we know that the variance is going to be the expected value of x squared minus the expected value of x squared, right? And we know that this has to be equal to 0. And so what we can say is that the expected value of x squared has to equal the expected value of x quantity squared. And we know the expected value of x here is 1. So expected value of x squared has to equal 1. All right? We know that the expected value of x also has to equal 1. Okay? So what is the probability that x takes on a value of 0? Okay, so let's suppose here that x can take on more than one different value, right? So we would have, say, px of 0 times by 0 plus, say, px of 1 times by 1 plus, and so forth. Okay? What are the two things that we know? Well, the first thing that we know is that the expected value of x has to equal 1, right? And sorry, I should be clear that what we're thinking about here is sort of taking the expected value of x squared. But if we had written down the expression for the expected value of x, right, it's going to look similar. Plus, and so forth. And so we know that this summation here has to equal 1, right? And we know that this summation here, this top summation and this bottom summation, both have to equal 1. Now, let's suppose, for the sake of example, that any of these values, the probability of x is greater than 0. The probability that x takes on a value of 0 is greater than 0. What that also means is that this value right here would have to be less than 1. Okay. Now, the issue that we're going to start running into is that at -1, or at 0 and 1, the expected value of x and the expected value of x squared are going to be the same, right? However, every other term is going to make this top summation bigger, right? Because what we're going to have here, if we just write out the first few terms here, right? 0 squared plus probability that x 1 times 1 squared plus probability that x is 2 times by 2 squared, and so forth. Right? And with the expected value of x, we're thinking about probability of x is 0, 0 squared. Or, sorry, not squared, just 0. X is 1 plus probability x is 2 times by 2, and so forth. Okay? So, here, we know that these two things sum up to be the same thing, right? But this term up here is going to be bigger than this term down here, right? Because you're multiplying the same probability, except these numbers, these squared numbers, grow to be bigger than the non-squared numbers. Okay. And so in order for them to be the same summation, right, we know that we can't sort of allow these terms to grow up, right? And so what we need to be doing is having these terms all go to 0. Okay, so that sort of leaves us to consider these two. And the issue that we're going to have is that both of these are just 1, right? And so we have the probability x is 1. And this is always going to be a little 0 term here. Okay? And so what we're left with is that the expected value is just going to have to equal the probability that x equals 1. And because of that, we know that this probability has to be 1, which leaves 0 probability behind to go here. Okay? So I sort of fear that that was unclear. I'll mark in that C is going to be the correct answer here, right? But I'll try to do this in sort of a slightly different kind of way here, right? Remember that the variance measures the squared distance of x from its mean, right? Or sorry, this should be the expected value, not the variance. And so what we need to do is we need to sum up over all possible values of x minus its expected value squared times by its probability here, right? And in this case, what we know is we know the summation has to be x minus 1 squared, probability of x, right? And we know that this has to sum up to be 0. However, this term right here is always going to be greater than or equal to 0, right? You can't have a negative value on that term because you're squaring it, right? Because of this square here. So because this can't be negative, the only choice in order to end up having this be a sum is to make it either 0 or to make the probability that x is 0, right? And so the only time that this is going to be 0 here is if x equals 1. So every other term has to have the probability of x being 0. Right? It doesn't matter what values we're summing over, they have to be 0, as otherwise the variance would be greater than 0. So hopefully that makes a little bit more sense there. But either way, if the variance is 0, we know it has to be a constant. Because the mean is 1, we know that that constant has to be at 1. And so C is going to be the correct answer. All right, last question here. Suppose that x and y are IID, probability of x and probability of y are the marginals. If y takes on a specific value, y prime, the probability of y prime equals 0.25, what is the probability that x takes on the same value? So what we want is the probability that x takes on the value of y prime, and what we know is that y and x are IID, means they're independent, means they have the same distribution. Because they have the same distribution, they have the same mass function, so this is going to equal probability of y, which is equal to 0.25. This is what we mean to say when we say that they're identically distributed. As a result, we know that this probability is going to be 0.25. All right, 1, since they're identically distributed, that's not what we mean by identically distributed. It means they share a mass function. 1 minus 0.25 equals 0.75, since they're identically distributed. Again, that's sort of not an interpretation there. 0.25 squared, because they're independent. Well, if what we were looking for was the joint probability, then we could start multiplying things, but we're not looking for a joint probability. 0.25, since they're identically distributed, it's exactly the right answer, exactly the right explanation, as 0 is incorrect. So that leaves us with D as the correct answer here. All right, and that's the entire quiz there. So I hope that helped, that provided some explanations to things, right? Of course, I would expect that, we could sort of walk through without the full explanation here. It would go through a little bit more quickly, but hopefully it gives you a sense of what is to come with the quiz. The quiz is going to be quite similar to this, so if you're feeling comfortable here, you should feel comfortable in the quiz. But of course, please do go look at the examples we've done in class, look at the examples from the course notes, sort of make sure you're asking questions and doing your full studying, but use this as sort of that final gauge, and then come in and sort of do your best on the quiz. That's everything that I sort of wanted to share today. So good luck with all of your studying, and I will see you in class during our next class.